If I asked you to walk into a massive, high-volume commercial kitchen and, point to the most hazardous spot in the room, you'd probably point to the open flames.
Right, or the deep fryers.
Yeah, exactly. Or maybe the prep station where a sous chef is moving a razor-sharp carbon steel blade at lightning speed.
Yeah, for sure.
We're practically hardwired to respect those physical, highly visible threats. Like, you touch a hot stove, you get burned. The causality is immediate and obvious. But if you walk right past the cook line and push through those swinging metal doors into the dish pit, you leave the culinary world entirely. You're now standing in an active, high-stakes chemical plant.
You really are, and that is a transition most people never consciously make.
No, they don't.
The environment behind those doors relies on a very precarious chemical equilibrium. When you look at the raw data, which we're doing today, you realize the hazards in a commercial sanitation setup are largely invisible, highly volatile, and frankly, just completely unforgiving.
Absolutely. So welcome to our deep dive. For this one, we are poring over a massive and honestly somewhat intimidating stack of safety data sheets, the SDS documents, and chemical reaction charts, specifically for commercial dishwashing and sanitation products.
It's quite a stack.
It is. Our mission today is all about chemical compatibility. We're decoding the precise, heavily regulated chemistry happening right under our noses in institutions around the world. We want to understand not just what these chemicals are, but the underlying mechanisms of, why they react the way they do.
Because in this environment, chemical compatibility isn't just some bureaucratic buzzword, right? It is the fundamental architecture of safety.
Right.
These aren't the mild, watered-down dish soaps you have sitting next to your sponge at home.
No, definitely not.
These are heavy-duty industrial formulations engineered to perform at extreme efficiencies. Like, a single deviation in how they're stored or mixed doesn't just result in a poorly washed plate. It can trigger rapid, catastrophic chemical reactions.
Okay, so let's unpack this. To really grasp the scale of the danger when things go wrong, we first have to understand the sheer power of the raw ingredients in this arsenal when they're working right. Like, the SDS documents paint a picture of just chemical extremes.
They absolutely do. Take a ubiquitous product like dishpit XP.
Oh, yeah.
On the surface, the label says it detarnishes and distains plasticware, but molecularly, it's an aggressive chemical powerhouse.
Right. It's not just soapy water.
Exactly. It's formulated with sodium carbonate, disodium metasilicate, and sodium carbonate peroxide. So you're looking at a highly alkaline salt combined with a very strong oxidizer.
Wow.
Yeah, it's designed to literally strip away organic stains at the atomic level.
And then you have the heavy lifters for the machine warewashing, like Solid Power XL, which relies heavily on sodium hydroxide. Now, most of you probably know sodium hydroxide is lye.
Yep, classic lye.
And when we talk about how lye cleans baked-on grease, it isn't just like lifting the dirt like a standard household surfactant. It's actually altering the chemical structure of the fat through saponification.
That is a crucial distinction. The sodium hydroxide attacks the ester bonds in the triglycerides, the fats, and it just severs them.
It literally breaks them apart.
Right. It chemically converts non-soluble grease into a soluble soap and glycerin, which can then simply wash down the drain. It is aggressively melting the fat into a new compound.
It's intense.
But to balance a commercial operation, you also need products on the absolute opposite end of the pH spectrum, like Keystone Limeaway.
The delimer. Because commercial dish machines get plagued by calcium carbonate scaling from hard water. And, standard soap does nothing to minerals.
Yeah, nothing at all.
So Keystone Limeaway brings in concentrated nitric acid and citric acid. The acids basically donate protons to the calcium carbonate, breaking it apart into carbon dioxide gas, water, and soluble calcium salts.
And what's fascinating here is the intentionality behind these extremes. The industry deliberately engineers these agents to be violently reactive.
Because they have to be fast, right?
Exactly. A commercial kitchen can't afford to let a pan soak in mild soap for 4 hours. They need that baked-on carbon and grease dissolved in 45 seconds. Right. The extreme reactivity is the feature, not the bug. But that exact thermodynamic instability is what makes the dish pit so incredibly dangerous if these opposing chemical forces ever cross paths.
Which brings us to the respiratory nightmares hidden in these charts.
Oh, yeah.
Because these products are designed for rapid chemical degradation, accidental mixing creates immediate, highly toxic byproducts.
Yeah, this is where it gets scary.
The most notorious incompatibility in the sources involves mixing a halogen with an acid. In the real world, this usually looks like someone accidentally mixing a bleach-based sanitizer like EcoSan or Ultrasan, which rely on sodium hypochlorite with that acidic dilemma we just mentioned, keystone lime away.
The chemistry of that mistake is just incredibly fast. The acid forces the sodium hypochlorite to decompose rapidly, stripping away the sodium and oxygen and liberating pure chlorine gas or Cl2.
That's the heavy greenish-yellow vapor, right?
Yes. It pools low to the ground. And the physiological mechanism of what chlorine gas does to the human respiratory system is, well, it's devastating.
Because it's not just that the gas itself is poisonous, it's what the gas turns into once it's inside you. Chlorine gas is highly reactive with moisture.
Right.
So when you inhale it, the Cl2 hits the watery mucous membranes of your respiratory tract and the delicate alveolar sacs in your lungs. And the gas reacts with that internal moisture to synthesize hydrochloric acid directly inside your lung tissue.
It's horrific. You are effectively inflicting severe internal chemical burns with every breath.
Wow.
The body's inflammatory response to that hydrochloric acid is profound. The cellular lining of the lungs becomes necrotic, and the capillaries become hyperpermeable.
Meaning they start leaking.
Exactly. Blood plasma begins rapidly leaking into the air sacs, a condition known as pulmonary edema. The victim essentially begins drowning in their own bodily fluids.
That is, the margin for errors are razor thin there. When you look at the OSHA safety thresholds, the numbers are completely sobering.
Oh, absolutely.
The ceiling limit, the absolute maximum concentration you should ever be exposed to at any given moment, is 1 part per million.
Just to contextualize that, 1 part per million is roughly equivalent to a single drop of liquid diluted into a 10-gallon tank of water.
That's almost nothing.
It's basically nothing. And the gas hits the IDLH threshold, immediately dangerous to life or health at just 10 parts per million.
But the heavy-duty dilemmas aren't the only trigger for these gas events. The sources highlight an incredibly mundane product that can be just as lethal: Reliance Glass Cleaner.
Right, because Reliance Glass Cleaner utilizes ammonium hydroxide to cut through glass smudges without streaking. It's an ammonia base.
And if that ammonia-based glass cleaner mixes with the sodium hypochlorite in the bleach sanitizers, the reaction doesn't produce chlorine gas, it generates chloramine gas.
Right, and the mechanism of injury for chloramine gas is slightly different but equally terrifying. It causes chemical pneumonitis.
Okay, how is that different from pulmonary edema?
So, unlike pulmonary edema, which is a fluid buildup, chemical pneumonitis is a diffuse, severe inflammation of the interstitial lung tissue itself.
Oh, I see.
The actual walls of the air sacs swell up, making gas exchange basically impossible. The threshold for severe damage here is astonishingly low, just 0.5 to 1 part per million.
Wait, so what does this all mean for the everyday worker? It sounds like spraying a mirror near a sanitized counter could send you to the emergency room.
That's exactly what it means. That invisible vapor hazard is exactly why the safety data sheets mandate absolute, strict chemical segregation in storage. You cannot keep the EcoSan on the same shelf or even in the same cabinet as the lime away or the glass cleaner.
Because even residual contact could be disastrous.
Yep.
But the horrors of chemical incompatibility aren't limited to toxic clouds. When we review the physical hazards in these data sheets, we find that these reactions can be violently structurally destructive. Like, I want to look back at the highly caustic detergents, Solid Power XL and Solid Silver Power.
Ah, the sodium hydroxide products.
Yes. The SDS explicitly warns that these bases are completely incompatible with reactive amphoteric metals, specifically aluminum, zinc, or tin.
Right.
If a worker puts an aluminum baking sheet into a sink full of this caustic pre-soak, the alkali rapidly dissolves the protective oxide layer on the aluminum. Once that layer is gone, the exposed metal reacts with the water in the solution to liberate flammable hydrogen gas, H2.
And hydrogen gas is incredibly insidious because it's odorless, colorless, and incredibly combustible.
Like Hindenburg.
Exactly like that. In safety engineering, we measure this using the lower explosive limit, or LEL. The LEL for hydrogen gas is just 4% concentration by volume in the air.
So if that sink is in a confined dish pit or under a low hood, and the hydrogen gas bubbling off that aluminum pan reaches just 4% of the ambient air volume, you have a literal bomb waiting to go off.
Yes. Any static discharge, the flick of a light switch, or a spark from a dish machine motor could ignite that pocket of gas.
You're turning a washing station into an unvented combustion chamber.
It's terrifying. And the sources detail other ways these chemicals feed combustion. Pathways drain sanitizer is a prime example. This product relies on peroxide blends like hydrogen peroxide or peracetic acid, which are extremely potent oxidizers.
And oxidizers are essentially the chemical agents that readily transfer oxygen atoms.
Correct. So if this drain sanitizer accidentally mixes with organic matter or strong bases, the peroxide bond destabilizes and rapidly decomposes. The byproduct of that decomposition is pure oxygen gas, O2.
Now, normal atmospheric air sits at about 21% oxygen. If that decomposition raises the ambient oxygen enrichment to just 23.5% in that local area, the physical rules of fire safety completely change.
Drastically accelerate, yeah.
Right, because oxygen lowers the activation energy required for combustion. Things that are normally incredibly difficult to burn suddenly become highly flammable. If a fire starts in a 23.5% oxygen environment, it burns with an intensity and speed that standard fire suppression systems often just can't handle.
It's a huge risk. But perhaps the most jarring physical hazard detailed in these sheets doesn't require spark at all. It's the sheer thermal energy generated by exothermic neutralization.
Oh man, this is pure thermodynamics. When you accidentally mix a strong acid, like the lime-away, with a strong base, like the solid power, the hydrogen ions from the acid and the hydroxide ions from the base aggressively bind together to form water.
Right.
But those ionic bonds contain a massive amount of latent chemical energy, and when they form, that energy is released into the surrounding solution as heat.
And the data warns that this exothermic release can cause an instantaneous temperature spike of 50 degrees Celsius, that's 122 degrees Fahrenheit, above the ambient room temperature.
Above ambient. So if that neutralization happens inside a sealed container or even a narrow drain pipe, the sudden heat can flash boil the surrounding liquid. The pressure spikes in a fraction of a second, the container violently ruptures, and it creates a concussive blast of boiling, highly corrosive chemical shrapnel.
It's a phenomenal amount of energy released in a very, very short window.
It's crazy.
But for all the drama of explosions and boiling acids, the sources detail another type of chemical incompatibility that is completely silent, entirely invisible, and incredibly dangerous to public health.
Ah, the silent saboteurs. This is where we get into chemical inactivation, and it completely shifts how you view a standard 3-compartment sink.
Totally.
In a commercial setup, the third sink is the sanitizer sink. The active ingredients in products like Oasis 146 multi-quat sanitizer or sanitizing wash and walk are quaternary ammonium salts, usually just called quats.
Right, and quats are brilliant examples of applied biochemistry. The quat molecule features a long, lipophilic tail that loves fat, and a cationic head, meaning it carries a positive electrical charge.
And since the cellular membranes of most bacteria carry a negative electrical charge, the quat is electromagnetically drawn directly to the bacteria. The tail pierces the bacterial membrane, disrupting the phospholipid bilayer, and essentially eviscerates the cell.
Exactly. But if we connect this to the bigger picture of the 3-compartment sink, the problem starts in sink number 1, the wash sink. That sink is full of dish soap, like Reliance liquid pot and pan detergent. To lift dirt effectively, most liquid soaps use anionic surfactants, meaning their molecules carry a negative electrical charge.
Here's where it gets really interesting. Wait, so you could meticulously scrub and sanitize a kitchen, do all the hard work, but because you didn't rinse the pot soap off before applying the sanitizer, the bacteria are perfectly fine, like the surface is still contaminated.
Yes, because if a worker doesn't perfectly rinse that negative anionic soap off a plate in the middle sink and dips it into the positive cationic quat sanitizer in the third sink, the two chemicals immediately seek each other out. The data sheets describe a 1.1 molar neutralization ratio.
So exactly 1 molecule of the negative soap binds fiercely to 1 molecule of the positive sanitizer.
Exactly. They lock together through electrostatic attraction and steric hindrance, forming a heavy, inactive quat anionic complex. It usually falls out of the solution as a faint, cloudy precipitate. The quat's positive head is shielded, its tail is tangled up in the soap, and it is completely neutralized. The acute danger here isn't chemical burns, it's the total loss of antimicrobial efficacy.
The illusion of safety.
Exactly. They did the labor, but the bacteria on the plate are entirely unaffected. You might as well have rinsed that plate in mud puddle.
That is deeply unsettling, to realize that you can follow the physical motions of sanitation perfectly, but fail completely because of invisible ionic bonds. It makes the rinsing step the most critical part of the entire operation. You aren't just washing away suds, you are physically breaking a chain of chemical neutralization.
And that fragility, the idea that you can easily kill your own cleaning agents, extends into some of the most advanced products in these catalogs. Sometimes the products rely on biology rather than raw chemistry.
Right, the biologicals. Pathways drain treatment is a fascinating example of this. You pour this down commercial plumbing lines to eat away grease clogs. But it's not a caustic solvent.
No, it's not.
The SDS reveals it is formulated with viable bacterial cultures and complex enzyme systems.
Specifically, enzymes like protease to dismantle complex proteins and lipase to sever lipid fats. It's an army of living organisms designed to digest the blockages.
But if a well-meaning worker decides the drain needs a little extra help and pours a strong disinfectant like bleach or a concentrated delimer acid down that same drain, they're initiating a microscopic slaughter. You are literally killing the cleaner.
Yeah, the bleach causes osmotic shock and physically lyses or shatters the bacterial cell walls. And the extreme pH of the acids disrupts the delicate hydrogen bonds holding the enzymes together, causing the proteins to denature.
Denaturing is essentially unraveling the tool, right? An
Yeah.
enzyme's ability to break down fat relies entirely on its precise three-dimensional folded shape.
Correct.
If you drop it in acid, the protein unfolds. It's like taking a meticulously folded origami crane and crushing it flat. It can never fly again. You turn a highly effective biological digester into a puddle of dead organic waste.
The systems are incredibly delicate. And because human error is inevitable, these data sheets don't just outline the chemical reactions, they dictate very specific, physiologically sound first aid protocols for when these compatibilities fail.
And reading these protocols really drives home the mechanics of the injuries. For instance, if a worker is splashed with a metal hydroxide or strong acetic acid, basically anything with a pH of 13 or higher, the protocol mandates continuous flushing with water for a minimum of 15 minutes.
And that duration is non-negotiable. Alkalis cause liquefactive necrosis. They don't just burn the surface, they actively melt deep into the fat layers of your skin through that same saponification process we discussed earlier.
Which is terrifying.
It takes at least 15 minutes of heavy water volume to physically dilute and wash away the compound before it melts through to the muscle.
But ingestion is where the protocols become really counterintuitive. If a worker accidentally swallows an alkaline salt, the sheets emphasize in bold print, "Do not induce vomiting." Instinctually, if you swallow a poison, you want to get it out.
But you have to think about the chemical mechanics. Alkalis are highly corrosive. When they go down, they burn the delicate tissues of the esophagus. If you induce vomiting, you are forcefully ejecting that same caustic chemical back up the throat.
Oh, man.
You're intentionally inflicting a second severe chemical burn on already traumatized tissue, dramatically increasing the risk of esophageal perforation. The protocol is to rinse the mouth, dilute if authorized, and seek immediate medical care.
The data sheets also prepare for atmospheric emergencies, specifically regarding carbon dioxide.
Right. In confined spaces, carbon dioxide acts as a simple asphyxiant. It physically displaces the oxygen in the room. When the concentration hits the IDLH limit of 40,000 parts per million, the physiological result is immediate hypoxia.
Your hemoglobin literally has nothing to transport to your brain.
Exactly. The mandated action is immediate evacuation and the administration of supplemental oxygen. You have to mechanically force oxygen back into the respiratory system to outcompete the CO2. This raises an important question, though. How do institutions prevent this? They obviously can't rely on a distracted dishwasher calculating molar neutralization ratios on the fly during a lunch rush.
No, they eliminate the human element almost entirely. The modern solution to chemical compatibility is the automated closed-loop dispensing system. These are engineered wall-mounted units that pull chemical concentrates directly from locked, sealed jugs.
The machines are internally calibrated to draw specific microdoses of chemical and inject them into a precise volume of water. The worker never touches the raw concentrate, and the machine physically prevents accidental mixing of opposing chemicals.
Most importantly, the closed-loop system enforces the golden rule of chemical dilution. Never add water to a concentrate. Always add concentrate slowly to water.
Right, the heat of dilution. If you pour a small amount of water into a large volume of concentrated acid, the rapid hydration energy released is massive.
Because water has a high specific heat capacity, right?
Yes, that small volume of water instantly absorbs the thermal energy and flash boils into steam, blasting the concentrated acid directly into your face.
But if you slowly add the chemical concentrate into a large volume of water, which is what the dispensers do, The large thermal mass of the water safely absorbs and dissipates the heat.
The engineering controls are brilliant, but they only work if the underlying chemistry is respected.
We started this deep dive thinking about the obvious dangers of a kitchen, the hot oil, the sharp blades, but what the safety data sheets reveal is a hidden, highly volatile matrix operating just behind the scenes. Dishwashing isn't just soap and water.
No, it's a high-wire act balancing explosive hydrogen, toxic chlorine gas, thermal heat spikes, and fragile biological cultures.
It truly is. Navigating the amphoteric metal reactions that generate explosive hydrogen gas, segregating halogens and acids to prevent toxic chlorine clouds, managing the thermodynamics of exothermic heat spikes, and ensuring the electrostatic charges of your soaps and sanitizers don't neutralize each other into useless precipitates. It is a brilliant, terrifying chemical ballet.
And when managed correctly, it is the invisible shield that protects millions of people from systemic foodborne illness every single day.
It is a marvel of industrial chemistry. But as we wrap up, it leaves me with a lingering thought I want you to mull over. We've just explored how these highly engineered, heavily regulated commercial cleaning products require strict isolation protocols, specialized protective equipment, and automated closed-loop computers just to prevent toxic catastrophes.
The commercial safeguards are immense because the margins are so tight.
So knowing the sheer power of these reactions, how much unknown volatile chemical mixing are you accidentally doing right now under your own kitchen sink with the everyday household cleaners you simply assume are perfectly safe?
It definitely makes you look twice at how you store your bleach and your glass cleaner.
It really does. The next time you reach for 2 different spray bottles to tackle a tough stain, remember the invisible, high-stakes chemistry happening behind those swinging restaurant doors. Catch you on the next deep dive.